Okay. Hi everyone. Hi. How are you? Good. Good. Any question? No? Everything's clear? Okay. Great. So let's continue. Last session we talked about reinforcement learning, but we couldn't finish it. So we will cover the rest of that. But before that, we also will review a bit the end of the last session, which was Q function and Q learning. So in Q function, we said let's use, rather than value V, let's use state action value Q. So I think I already told you that in reinforcement learning, for you to understand it well, you should know the essences of the variables or the things that are existing in reinforcement learning. And for example, this essence, they call it with different names. For example, in physics, they also call it dimensions. So the dimensions or the essences of the two sides of equation should match with each other, especially in physics, right? If, for example, you have an equation in physics where the left-hand side is kilograms per second, the right-hand side should also be in the dimension or essence of kilograms per second. Also, I'm saying that in reinforcement learning, at least this is how I could understand it. For you to understand it well, you need to understand the essences of things in reinforcement learning. We have two main essences. One of them is reward, the other one is action. Okay, at least two main essences. So we learned in the last session, we learned various things. Three things with the essence of reward and two things with the essence of action. What were the things with the essence of reward? Can you tell me? You remember? One of them is reward itself, R, right? Another one is value. What was value? According to the Bellman equation, it was the largest value, the largest reward that we can get, right? The largest reward and discounted rewards that we can get according to Bellman equation. The third thing, which has the essence of reward, is Q function. Q function. And what is the difference between value and Q? The value V is only a function of state, as you see. But Q function is a function of both state and action. In other words, value V says what is the best reward that I can get in this state, right? But Q function doesn't say the best reward. It says in this state, if you do this action, what is the reward? Okay. So as I said, all of these have the essence of reward. Reward, value, and Q function. What about action? Action is another essence, right? So there are two things that have the essence of or dimension of action. One of them is action itself, A, right? The other one is policy. Policy, because the output of policy is action. The input of policy is state. The output of policy is action, right? The policy says in this specific state what action I should do. Okay, so 5 things we learned, 3 of them in the essence of reward, 2 of them in the essence of action. Now, so we talked about value and Q, and we said that V is called state value or value, Q is called state action value or Q function. And we said that whatever we learned for value, we can have it for Q function because they have the same essence. So for example, we had Bellman equation for value V, so we can easily have Bellman equation for Q function. Compare these two, right? Also in the Bellman equation, we can have the optimal value. For optimal, we use a star, superscript star in reinforcement learning, right? So here we put V star in the Bellman equation. Likewise, we can have Q star in the Bellman equation. Also, in Bellman equation, we had this for value, right? and this is Bellman equation for Q. Can you tell me why? So here I have replaced V with Q. Vs is replaced with Qs and A. But here, Vs prime has been replaced with maximum of Qs prime and A prime. Can you tell me why maximum with respect to A prime? Yes. Yes, yes. So let me rephrase what you said. Thank you. So here we have value of S prime, which is the maximum reward at S prime, right? Because value is maximum reward. Here, Q S prime, A prime, for every A prime, it has some reward. One of them is the maximum reward. So I need to have maximum of Q with respect to A prime, right? Okay. And then we said, if we maximize Q star S and A with respect to A goes away, right? You have this function, you maximize it with respect to A. So the variable A goes away. The only thing which remains is S. As a result, it becomes V value, right? V star. What about argmax of Q star with respect to A? We know that argmax of something with respect to A should be in the essence of A, action. So it's policy, right? So maximum of Q is in the essence of reward, value. Argmax of Q with respect to action is in the essence of action. So it's policy. So it's easily you can see that the essences of the or dimensions of the sides of equation match, right? So also here, I have argmax of discounted rewards. If with respect to pi policy, so argmax of this with respect to pi, as the optimization variable is pi, is in the essence of policy or action. So it gives you policy star, right? What if I had only maximized this with respect to pi? It would be in the essence of reward or value, right? Then we said, do you remember incremental update or temporal difference that we had for value here? Again, as I said, whatever we have for value, we have it for Q too. So here we also can have it for Q, like before. And the GN, if you remember, it was the total discounted rewards, right? And we said we can have policy iteration using Q function. Do you remember policy iteration? So policy iteration has two steps: policy evaluation and policy update, right? And we alternate between them. I remember I told you, forget this algorithm. In real life, you want to improve something. What do you do in real life? You evaluate it, see how good it is, then you improve it. By improving that, it changes. So you need to evaluate it again. Then you see how much it changed. Hopefully it's improved. Then you improve it further. By improving further, it changes again. You need to evaluate it. So you need to alternate between evaluation and improvement until it doesn't change anymore, until it converges. This is exactly what we are doing here. So you do it for whatever you want to improve in your life, right? So you do it now for Q function. So you evaluate policy, then you improve policy. Then you evaluate policy, improve policy until it doesn't change anymore or doesn't change drastically, right? So now you tell me, for how can I evaluate the policy? Assume I have some policy. Yes. Exactly. So based on how good the value or reward or Q is, right? Right? So do you remember in policy iteration using value V in the previous slides, in the previous session that we had? We evaluated using V, right? Now we are gonna use Q function. So we evaluated using Q. The greater the Q, the greater the reward, the better the policy. Likewise, previously we had the greater the value V, the better the reward, the better the policy, right? Agree? So here we use the temporal difference of Q to evaluate the policy by Q. the greater the Q, the better the policy. And then we say argmax of Q with respect to action. We know that it is in the essence of action. So it gives me the policy, right? Then we talked about Q learning. What did we say? We said, do you remember we had, this was the Bellman equation for V value, right? And then we said, do you remember in temporal difference, we approximated the Bellman equation using one sample. So it became like this, right? And likewise, again at this. Which one? No, it's not GN. This is GN. GN, do you remember it was the total discounted rewards? This is it. Okay, used in the temporal difference, right? Here we have it. Here we have it. Now, what did we say? Okay, so again, I repeat, whatever we have for value, we can have it for Q2, right? So we had this for value V, now we can have it for Q. But we should note that here I have V, I replace it with maximum of Q with respect to action, because value V is the maximum reward, okay? And now this is the total difference that we had. Now the GN, do you remember? This equation was the incremental update. Do you remember in the previous session, what was the difference between incremental update and the temporal difference? Let me go back for you to remember, if I can find that slide. Here it is. For value V, this was the incremental update. And then we said, let's replace GN with Bellman equation approximated by Monte Carlo approximation using only one sample, right? And then we replaced GN with this, and then we called it temporal difference. Okay, okay. Likewise, I'm gonna use this. So in this slide, where was that? In this slide, these are incremental updates of V and Q. Also, we use that in the policy iteration using Q function. Now I'm gonna discuss temporal difference for V and Q. So this was temporal difference for V and Q. If you remember, I haven't written that. So this was used in the temporal difference of value in the slide that I just showed you. And now I'm gonna use similar to that rather than G in the incremental update. Rather than this, right? And then I get this. Everything is the same as before. I'm just replacing value V with Q, but I'm also noticing that value is the maximum reward, right? So I replace it with maximum of Q with respect to action, right? What is this doing? What is this saying actually? This is saying that this is my Q function, my reward in the future, in one step ahead in the future, right? Because it's S prime and A prime. I said prime means T plus 1. But I'm maximizing with respect to A prime, my next action. Basically, it means that the next state that you go, what is the best reward that you can get in that state, right? Okay. This is used here. And we discount that also by gamma. So what did we say here? And now, do you remember this V used in update of V in value iteration? In the previous session, we had that. You can compare that. Here we are using Q. Previously, we used V. Where do you remember value iteration and policy iteration were used in Markov decision process? You remember that? At the start of the last session. What was the difference of Markov decision process and reinforcement learning? Yes. Yeah, but which probability? For the state transition. Yes, exactly. Thank you. So in the Markov decision process, we know the transition model from one state to another state, right? But in reinforcement learning, we don't have it necessarily, and this is more realistic scenario, right? So value iteration and policy iteration were used for Markov decision process. Q learning and this temporal difference of Q is used in reinforcement learning. Can you tell me why do we use Q learning for reinforcement learning, but V suffices to have in Markov decision process? Intuitively, I mean. Intuitively, it makes sense because in Markov decision process, I have more information. So value depending on state S suffices for me for calculation. But in reinforcement learning, I need to consider all scenarios, all cases, right? And the Q is a function of both state and action. For different actions, you take care of calculations. But in Markov decision process, you only consider the maximum reward, the value, right? So and intuitively, I'm saying that compare these two. Okay. And Q learning, nothing scary, very easy. What in real life, forget math. In real life, you have something and you assume you can change it. How can you change it? So what do you do usually? You make a for loop, you make a loop, and you change that thing to make it better and better and better until it doesn't change. And you say it converges, right? This is exactly what we're doing. I gave you this example. I said a for loop of assume you want to change Ben, you want to change me, okay? So you change Ben, the previous Ben plus some delta, and this delta changes in every loop, right? Plus some delta, you replace the previous Ben with the new Ben plus delta, right? So the new Ben becomes the previous Ben plus delta, and the delta is changing in every iteration. You go and hopefully Ben gets better and better until the previous Ben and the new Ben will be almost the same. Delta becomes almost zero, right? This is exactly what we are doing in Q learning. Replace Ben with Q. So next Q is the previous Q plus some delta. And you also have alpha N to scale it down, right? It's alpha, that's why alpha is called learning rate, right? And this is a delta. And this delta, initially, if Q is awful, it's large. Then this delta becomes smaller and smaller, right? Especially by getting better and better, by Q getting better and better, until it converges. What is this doing? Can you tell me? So it's finding the Q function for state S and action A, right? When you find the Q function, of course, iteratively we are doing that. When you find the Q function for state S and action A, it means that you can compare the actions in a specific state, right? Assume you have 3 possible actions in the specific state S. You calculate this QSA for all of these 3 actions. The action which has the larger Q, it means that's the better action, right? In that state. And interestingly, it is just finding Q by interacting with the environment. It doesn't have a transition model. This is a miracle. By just experimenting, like a baby, like a newborn baby, which doesn't know anything. The baby tries out the world, right? And finds out what is the best thing to do. Probably at the start, maybe it goes toward the fire, but it senses the heat. Next time it won't go toward the fire, right? It tries, and by trial and error, it finds out what is the best thing to do. Okay. Then I said, how do we find the action A for this Q learning? There are two things, right? 2 concepts, exploration and exploitation. I said we can select the action A randomly, right? By doing that, I will explore whatever I can do in this environment, right? In this state of the environment. Or I can find the best action the best action in this iteration. What do I mean? Because Q, S, and A is changing, right? Maybe for a specific state S, the QSA1 is better. In the next iteration, QSA2 gets better because QS and A is changing, right? So when I say the best action maximizes the Q function in this iteration, okay? But when we do that, we don't explore the different actions. We only do specific actions, right? In other words, we might get stuck in the local best. Maybe in initial iterations, some QSA is larger and we will only get stuck in that. We'll not explore other actions for that state, right? But it will converge faster. So it's a trade-off. If we find the best action only, it will converge fast, but we don't trust that answer because it might get stuck in the local. But if we do it randomly, it convergence will take time, right? It will be slow to converge. But we are exploring which one is the best thing to do, to have both of them, kind of. That's why there are several ways to do that. First off, like what we discussed in methodistic optimization, we can first start with by exploring, and then in the later iterations we can just exploit, right? Because in the later iterations I don't want to oscillate around my solution. I'm supposed to be close to my solution. Something that I didn't say in the previous session was this. There is an algorithm named epsilon greedy, which does this with probability epsilon. It takes random action with probability 1 minus epsilon. It does the best action. So basically it does both of them, right? This algorithm is called epsilon greedy. Why is it called epsilon greedy and not 1 minus epsilon greedy? Because when you do the random action, you are greedy to explore, right? It's the greed of you to explore the space. And also, so this probability, now you tell me, we can change this probability, this epsilon. In initial iterations, epsilon can be large. In the later iterations, we can decrease epsilon, right? Because initially you want to explore more, gradually you want to exploit more, right? We showed some example. This example is called also a random walk, this game, because you randomly walk between states, right? This is a 2D random walk. We can have or 1D, whatever we call it, 1D. We can have 2D random walk, 3D random walk, right? So depending on how the cells are put to each other, next to each other. And then I gave you some example of how Q function is changing. For this specific example, for example, of course, in this game, going to right is better because it will win. Going to left is bad because we will lose, right? Right? And that's why when we went right, QD and right got improved from 16 to 17. It makes sense because we are going right. Someone told me after the session that what if our Q, for example, here it is 16 and 10. What if it was 10 and 16? It wouldn't make sense, but we can have it. In this case, delta would be large, right? Large. So the delta in Q learning will make it in a way that after many iterations, it makes it in a way that it makes sense, right? Initially, it might be 10. For right might be 10. For left might be 16. Do it for many iterations, and you will see that right will improve, increase. The left will decrease. And this is training, right? And this was just one iteration of training, of Q learning. What should you do in the test phase? What do I mean by test phase? Is I want to train it, and then I want to use it for playing the game, right? Right? So in the training, you will learn it for this specific game. What would you expect? Q of B right, C right, D right, E right, F right. All of them will be very large, maybe 20, 30, right? After convergence. Q of B left, C left, D left, E left, F left will be very small, such as 0 or 0.1. I'm not sure whether it can get negative or not. Anyways, it becomes very small, okay? Right becomes large, and left becomes very small. And then you tell me, now in the test phase, I start with D. What should I do? At every state, I should choose the action with the largest Q. Did you understand? So when I'm at D in the test phase, what do? I compare QD right and QD left. Of course, QD right is larger after training. So I go right. Then I go to state E. QE right, QE left. QE right is larger. Go right. QF right, QF left. QF right is larger. Go right. You go to state G and you win the game. Did you see that? And by the way, this was one iteration of Q learning training, right? Then I said, do you remember the temporal difference for Q function? It was this, right? Then I said, let's approximate the Q function with some function. That's why they call it Q function, right? So let's approximate it by some function, and this function can be linear or non-linear. What is a good example of non-linear function which approximates other functions? It's neural network. It's a non-linear function which approximates some behavior, right? So as a result, I can approximate my Q or my Q's behavior by a nonlinear neural network. And why is it nonlinear? Because we have nonlinear activation functions in between the layers, right? If we don't have any nonlinear activation function, the whole network is a linear projection, because you can see every layer as a linear transformation without any activation function, I mean. But when you put nonlinear activation functions such as sigmoid or ReLU or whatever in the middle, then it becomes nonlinear. Okay, then so we can replace that. Now for the neural network, we need to have a loss function to minimize, right? So now we are in the head of the designers of some algorithm named DQN, Deep Q Network. Okay, they were the employees of DeepMind. Okay, they were in UK, a small company in UK. They were not in Google at that time. Okay, they said, okay, we have Q learning, we have the temporal difference of Q. Let's train some neural network which does that for us. Okay, what did they do? So they said, okay, apparently this has two parts, this part and this part, right? You can see it as this minus this. This the delta thing. This is the delta, right? That I was talking about. I desire this delta to become 0. Delta almost 0 means convergence of Q, right? And so let me minimize this delta. So this loss initially, this delta is initially large, but gradually it decreases until Q is converged, right? So as a result, they define the loss with what is W? The parameters, the weights of neural network, okay? And for difference, it's better to use, because you can see this is a float value, right? It's not an integer value, right? This delta. So it's a regression problem, okay? What do you want to do? So you want this, the value of this, to be very similar to the value of this. You have different options. One might say, let me use L1 norm difference. When one may say, let me use Euclidean distance, L2 norm, a squared Euclidean distance, a squared L2 norm. So that usually in the literature, they use mean squared error, or that's almost a squared L2 norm or a squared Euclidean distance. What do I mean? So this one minus the other one to the power 2. Why to the power 2? Because the sign is not important, right? And I also have 1/2 here. Why? Because when you take derivative, it's optimization, right? When you take derivative, I have power 2. X to the power 2 becomes 2x. So I want to get rid of that 2 in the derivative. So I put 1/2 here. Okay? Did you get it? So we use usually mean squared error for these kinds of things. Again, why? Because these values are float. They are not integer. Otherwise, we would probably use cross entropy. It isn't classification, it's a regression problem. Okay, now, so this simple idea became a paper in, I think, either Nature or Scientific Report, one of the biggest journals in science. Okay, and that's why Google bought them for millions of dollars, and now DeepMind is a part of Google. Okay, so what did they do? So this is the derivative with respect to W. This is quadratic with respect to W, right? But we also said that there is a problem. I think they faced these problems in practice. So they had this network. They use Q. Sorry. They use Q in both of the. So what did they do initially in DeepMind? They said, okay, I have this Q. This is a network, right? Q is the output of network. We also have this Q. So I'm using the output of network twice. They trained it and they saw that they can't converge. And then they had a meeting and they thought about it. And they said, of course it shouldn't converge. Why? Because you have two parts, part 1 and part 2, right? Part 1 is trying to chase part 2, so their difference becomes almost 0. But when part 1 moves, part 2 also moves. Because you're changing both part 1 and part 2. So it's like one person chasing another person, but that person isn't standing. That person is also moving. You never reach that. You may reach it by chance, but you usually don't reach it. Right? So they said, what should we do? There are two solutions in the literature for that. One solution is this. Let's keep that second person fixed. Right? Don't change the second person. As a result, let's use two neural networks. One for the first part and one for the second. Right? So we have two networks, one for this Q and one for this Q. So let's call this Q the network of part 2. Let's call it target network. Because this is our target, we want to reach it. And the first one is the Q value estimate network, the network which estimates or approximates our Q function, right? And then we only now by backpropagation, by learning, we only change this Q network, right? Not the target network. But the target network in the original formula needs to change also, right? So let's relax the problem, and after every k iterations, we update it once. So it's a middle case scenario, not holding it forever. After every k iterations, let it move a bit. Okay? So far clear? So that was this first solution, using two networks, or one of which is target network. The second solution is called experience replay. What is it? So it says that the previous experiences. So what is the experience in reinforcement learning? This current state S, current action A, next state S prime, the reward in this current iteration R, right? Whatever you do in reinforcement learning, this is your experience. Now, when at every iteration, always keep track of these experiences, right? Okay. Now in every iteration, when you want to train by backpropagation, what do? You take the mini batches from the previous experiences. right? When you do that, what happens? You're kind of using a log of history. So you don't oscillate much. You don't change much. In other words, your target network doesn't change drastically because you are using your previous experience. I know it's a bit heuristic, but it makes sense, right? Because you're using your previous history that you used also for this target network as well. So here in this experience replay, I don't have two networks. I only have one network for both Q functions, okay? Only have one network, but the network for this second Q doesn't change a lot, right? The network for both of these Qs doesn't change a lot. As a result, I can hope that it converges because I'm using my previous history. We saw similar thing in the previous sessions where, you remember, I said when we use momentum. Momentum. Do you remember momentum? We talked about it in the PSO lecture. Also, I said that it is used in neural network deep learning as well. Momentum. You don't remember it? So momentum was using a log of history, and I showed you both by intuition and by mathematics that it dampens the oscillation of gradient descent, right? Likewise, we have the same idea in experience replay. Okay, so one of them is using two networks, the other one experience replay. By the way, both of them don't have any theoretical proof for convergence. So we just hope in practice, they usually converge. And let me tell you that there are two things, there are famous two things in the literature of machine learning that they are known to be hard to converge. One of them is reinforcement learning networks. The other one is GAN, generative adversarial networks. When you are working with them, you need to be very patient, right? RL networks might take days to start showing that they are converged. Okay. So you need to be patient. By the way, I heard that when they were training DQN, it wasn't converging. It wasn't converging even with these techniques that they use for, I think, days or maybe a month. But they had hope. They knew that it must work. So they waited. They waited until it converged. Okay. So now I said the first paper which implemented gradient Q learning using a deep neural network was DQN, short for Deep Q Network, proposed in 2013 by DeepMind. This paper was also considered as the first algorithm in deep reinforcement learning, or DRL, yes. You're sampling your mini batches not from your new data, from the previous experiences. Maybe in initial iterations, of course, you don't have any previous experience. Train it for a while. Of course, it will oscillate a lot because the first part and the second part in the last function will change a lot. It will oscillate a lot. After a while, start sampling your batches for training only from the previous experience. Then it will not change a lot. So it will converge. Okay. For the experience replay, I said that. So DQN was the first algorithm in deep reinforcement learning. And what is deep reinforcement learning? It's nothing complicated. It's just the reinforcement learning where Q function or value function or policy function is estimated using a neural network as an estimator function or approximator function. Because we have a bunch of functions in reinforcement learning, right? A function which tells you the Q, a function which tells you the value V, a function which tells you the policy pi. Each of these can be approximated by a neural network, a nonlinear neural network. If you do that, it's called deep reinforcement learning because you're using neural network. Therefore, DRL is basically not different from RL, except that its function estimator is a neural network. Okay. Now, how did they impress the reviewers and the people? and especially Google, how do they impress them? So they played Atari games. So what did they say? Do you remember? I don't know if you remember Atari games. Sega, Atari, good times. So Atari games, what do they do? So they said, okay, let's have the frames, every frame of Atari game at every time step as one state, right? So it's an RGB image, right? An image with 3 channels, red, green, and blue. And you give it to the neural network. And as it is an image, you need a convolutional neural network for training that. So what is convolutional neural network? Let me tell you briefly if you don't know that. Do you know that? Okay, what is that? Fully connected neural network, assume. So I have these neurons, right? Assume I have a bunch of neurons, right? And then I connect, so I have a bunch of neurons in the next layer, a bunch of neurons in the next layer. So I connect these neurons to each other. Every neuron of a layer is connected to every other neuron in the other next layer. Okay, the neurons of the same layer are not connected to each other. So basically I have this, something like this. And also like this, right? This is called fully connected neural network. Okay? And so on. And each of these is a layer. At the end of every layer, I have a bunch of nonlinear neural net, nonlinear activation functions, nonlinear functions. Okay? This is called fully connected neural network. Now you tell me, assume I have an image. Assume I have, are you listening to me? Are you looking at me? So I assume I have an image. And I want to feed it to the feed-forward neural network. This is called, it has several names. Fully connected neural network, feed-forward neural network, multi-layer perceptron. All of these mean the same thing, okay? Now you tell me, what should I do? So these are pixels of image. I should, of course, reshape it to become a vector so I can feed it to this, because this is also a vector, right? So how do I reshape it? Take the first row of pixels, then the second row, concatenate it, then the third row, or do it column-wise, doesn't matter. Okay, and so you do this, but you are ruining some information by this reshaping. Why? Let me tell you this. Consider a small image, pixel 1, pixel 2, pixel 3, pixel 4, 5, 6, etc., 7. Let me reshape it. It becomes 1, 2, 3, 4, 5, 6, 7, etc. Right? 1 and 2 were close to each other. Here also 1 and 2 are close to each other. That's fine. That's good. But 1 and 4 were also close to each other. But here 1 and 4 have distance from each other. 1 and 5 were close to each other. But now 1 and 5 have distance from each other. So you ruined the spatial correlation between pixels. Only some of them were preserved. Right? Agreed? So as a result, people said, let's not ruin the structure of the image. Let's change the structure of network. So they said, rather than this, let's have a, have you passed any course on image processing? No? So you have a filter. What do you do? There are a lot of things that I'm saying that, but I have to for explaining convolutional neural network. By the way, I have videos on convolutional neural network in my YouTube channel. Feel free to watch them. I'm just saying this very fast for you to understand what this means. So I have the image, and then I convolve some filter to the filter on this image. Okay. As a result, I haven't reshaped my image, but I have changed the structure of my neural network. This is called convolutional neural network because I'm convolving some filter on the image. And let me tell you very fast, but for more details, see my YouTube channel, please. In image processing, the filter, so for example, this is the filter. The filter is usually fixed. What do I mean? For example, I want to extract edges. Okay. What is edge? You know what is edge, right? In the image, right? I want to extract images. So what can I do? This filter works. -1, -1, -1, 1, 1, 0, 0, 0. Why? Because consider some wall here. Assume it is wall. Here there is background of wall. There is no wall here. Okay. Wall is dark. Background is light, bright. Okay. Then what happens? If my filter, this filter comes on this edge, what happens? The value of filter becomes large. Why? Because -1 times a small value, a small intensity, plus 1 times large intensity, brightness, becomes large, right? So basically, this -1 and 1 is capturing the contrast between two adjacent pixels, right? Right? So as a result, this can extract the edges. We can also have some filters for smoothing the edges, some filters for exaggerating the edges, right? Sharpening the edges. Now, convolutional neural network says, let these values of filters be learnable parameters. Let's learn them by optimization. Who says that they should be fixed? Let's learn the filters for our own task. And the task might be classification, might be regression, whatever. For decreasing my loss function, let me learn the values of filter, right? This is what convolutional neural network does. Where were we? Okay. Here, we have the frame of Atari game. And as I said, we don't want to reshape it. So we use convolutional neural network. And in convolutional neural network, usually we have a bunch of convolutional layers, and then we have a bunch of fully connected layers. I introduced both of these just minutes ago, okay? Why do I have to have fully connected layers at the end? I have to have. At least one fully connected layer I have to have. Because at the end, I want to do classification here, okay? What do I mean? Assume I have how many? So every action on the joystick of the Atari, okay, is one class, okay? Going up, down, right, left, kick, whatever, okay? So we have these many actions on the joystick. You can see it as buttons of the PlayStation console, whatever we call it. Okay, so now we have these many classes. So I'm gonna use softmax. I already have explained softmax to you. Do you remember in this course? Do you remember? exp of xi over summation of exp of xi. I remember I told you that I have a bunch of values, scalars. I want them to behave like probability. Then I said, what can I do? I can divide each of them by the summation of all of them. Then they will become between 0 and 1, and they will sum to 1. But I said, what if I want them to behave like Gaussian distribution, Gaussian probability? In the Gaussian distribution, I have exp operator, exponential operator. So let me put them in exponential operator and then divide them by the summation of them. This is called softmax form. They sum to 1. They are between 0 and 1, and they behave like Gaussian distribution, right? So we use softmax activation function at the end. Okay? And as you see, this is a vector. Up to here, I had convolutional layers. Up to here, it was image. That's why we have to have at least one fully connected layer at the end to reshape the image to vector. Okay? Are you following me? Now, what do I do in training and also in the test, that in both of them? So I have softmax form. I have frame as input, frame of game. Do you agree that they will sum to 1 because of softmax form, and they are between 0 and 1, and one of them is larger than the other one, right? One of them will be larger, meaning that action, so because each of these corresponds to some action on the joystick, it means that one action for this specific frame will have more probability. So it determines what action I should do in this frame. Now this action might be awful. This predicted action might be awful, might lose the game. What happens if that happens? The loss will be large. If I choose a very bad action for that specific state frame, this loss, this will be very large. So by gradient descent, I will update it significantly, saying that what you did was awful, don't do it again, right? What if I do, because initially I'm playing randomly, right? The network is playing randomly. What if randomly it does some good action? Then this loss will be small, and it will not change much. It says whatever you have in your network is good. Do you see how it is working? By the way, you might be saying that this is one step of gradient descent, right? Recall preliminaries, I think. I talked about gradient descent, right? Why am I saying that this is backpropagation? You know that neural network has a lot of training algorithms. The most famous one is backpropagation. You can see this as both backpropagation and gradient descent. Why? Yes. So basically, let me tell you this. In other words, backpropagation is nothing but gradient descent and chain rule. So backpropagation and gradient descent are the same thing, but in neural network we need a lot of chain rules, because every weight depends on the weights of next layer for when you are backpropagating the error. Why is it called backpropagation? Because we are propagating the error from the last layer to the first layer. Where is the loss? In the last layer of neural network. Okay. Again, if you didn't understand some parts of these, either ask me or watch my YouTube channel. I have a course on deep learning, right? And I have said, I have put titles on them. You can see which part you need more explanation, and you can watch them. But feel free to ask questions on Piazza, and I will be happy to answer. So this is DQN. And it impressed people. Why? Because after training, it could beat humans in playing Atari games. Okay. Now, policy gradient. So Q learning that we talked about is a model-free, value-based method, right? Because it's based on Q. It's model-free. We already talked about it in the previous session. Model-free and model-based RL, right? In Q learning, the value function or Q function, what is it? It's explicitly learned, right? Because we are learning the Q. But the policy function is implicit. We never learned the policy. Now we have another algorithm named policy gradient. What is it? It's the other way around. It learns the policy explicitly, the policy function, but the value function or Q function is implicit. By the way, both of them, both of Q learning and policy gradient, are model-free, but one of them is value-based, the other one is policy-based algorithm. Okay? Clear so far? Now, both Q learning and policy gradient pursue the goal of RL. What was the goal of RL? Finding the optimal policy. Finding the optimal policy. Okay. The policy gradient attempts to learn the policy function explicitly, as I said. We want to learn the policy pi. So The policy pi, do you remember I talked about it in the previous session, is either deterministic or stochastic. Deterministic means not random. Stochastic means random. Probabilistic, I mean. So if it is not random or non-probabilistic, deterministic, for every action, for every state, you have some action. It's like a function, right? But if it is a stochastic, then you have a probability distribution, conditional on the state. Okay. By the way, I will not ask in the exam questions that are, for example, related to deep learning and these things. So you don't need to worry about that. Just, but also in the last session, which is the next week, I will also give you some hints on what to study more for the exam. Don't worry about the exam. With peace of mind, learn. The goal of the course is learning. Like the goal of RL, which is finding the best policy, the goal of the course is learning, right? It's not grades. Okay. So because I sometimes see stress in your faces, I don't know why. Because at least this course is not for stress or pressure. This course is for learning with joy. Okay. Now, so I want to, in policy iteration, I want to learn policy. Now, did you notice that in Markov decision process, we had two main algorithms, value iteration, policy iteration. In reinforcement learning, we have two main algorithms, Q learning, policy gradient. By the way, for Q learning, they also call it gradient Q learning, right? Gradient Q learning and policy gradient, right? So here, I'm talking about policy gradient. Then what do? Each of these policy functions, the either stochastic or deterministic, have their own pros and cons. Yes. No. In Q learning, we'll never learn an explicit policy. Yes. So in Q learning, we are learning Q, but using Q, we can find the action. So for example, we learn Q SA for every state S, different actions A, right? I learned their Qs. Then simply I can say argmax Q SA with respect to A, it gives me the policy or the action, right? But I never used pi. That's why I'm saying that the policy is implicit. I'm using Q, right? No, I first learned this using gradient learning. Do you remember? I first learned this Ben equals Ben plus delta. That was the Q learning, right? So I learned Q, and then I can use Q for finding the best action. Okay, I haven't yet explained policy gradient. But I'm saying that in policy gradient, I don't learn Q. I learn the policy pi. Okay. So a stochastic and deterministic policy, they have their pros and cons. The deterministic function is usually used for discrete, is a discrete function, but a stochastic policy is usually a smooth and continuous. Why? Because for a stochastic, you can use probability distributions, and they are usually like Gaussian distribution. They are smooth and continuous. But for deterministic, you usually use discrete function. So as a result, a stochastic policy, if it is smooth, it's good for learning because smoothness is good for gradient descent and gradient optimization, right? Also, if the action space is continuous, that would be suitable to use probabilistic policy. But anyways, in general, we can the probabilistic or a stochastic policy can be either discrete or continuous in general. If it is continuous, I can use like Gaussian distribution. But what if it is discrete? As always, we use softmax, right? To make it behave like Gaussian distribution, right? Okay, by the way, this is the mean of the Gaussian distribution. This is the covariance of Gaussian distribution. And as you see, they're all functions of W. W are the parameters of this policy. If I estimate my policy by a neural network, this W becomes a weights of neural network. Okay? Now, we can have supervised learning. What is supervised learning? I mean classification. Okay, in this case. Classification or regression, doesn't matter. Anyway, supervised learning, we have labels in it. Okay. I want to compare supervised learning with policy gradient in reinforcement learning. First, let's talk about supervised learning. Assume I have some labels. What are the labels here? You tell me. So I have some states, and for this state, I have the best action. Right? So I have a bunch of states, S1, S2, S3, etc. Right? And for each state, I know what is the best thing to do. The best action, A1 star, A2 star, etc. Right? So this simply becomes, let's call it regression problem. Because for every input S, I want to predict action A, or classification problem. Doesn't matter. I want, for every input S state, I want to predict the action. Right? So I can use any loss function for supervised classification, such as cross entropy. Okay, there are a bunch of methods to do that. But another way to do that in supervised learning is we have a probability, right? A probability of policy, right? And this probability is also supervised here, because for given Sn, what is the probability of best action, An star, right? So let's maximize this probability. In other words, it's called best maximize the log likelihood, right? It's like a likelihood, and I use log likelihood. Why do I use log likelihood? I think I have said it in this course. For two reasons, we usually use log likelihood. But whenever I say likelihood, I mean probability, log probability, logarithm of probability rather than the probability. Why? For two reasons. First, many of the probabilities that we have normalized, maybe that's the third reason. Okay, maybe we want to normalize it not to become too large, but I have two other reasons in mind. First, many probabilities are in the exponential family, such as Gaussian distribution. Recall the PDF, probability density function of Gaussian distribution, right? They have exp in them. The exponential operator is a pain in the neck. Let's get rid of it. So we use the opposite operator, which is logarithm. Logarithm of exponential operator becomes the argument, right? They cancel each other. The other reason is that usually my data is IID, independent and identically distributive, right? When I have a bunch of IID data, the joint probability becomes the probability of each of them multiplied by each other. So just one multiplication of probabilities. Right? Multiplication is a pain in the neck. So I use logarithm behind that, because I know that logarithm of multiplication becomes summation of logarithms. So for converting multiplication to summation, I use logarithm. For these two reasons, and maybe the third reason that you mentioned, not to normalize it, not to become too large, we use logarithm, right? Logarithm of this. So we maximize this, right? As a result, I need to use gradient ascent. So this is plus, not minus, because gradient ascent maximizes rather than minimizes. Now you tell me, if I want to implement it in a neural network, what should I do? Because in neural network, I can't maximize. I need to minimize according to the libraries of neural network. I simply, so the neural network here is minus, I simply put minus derivative rather than plus derivative. Because I know that, you tell me, maximization of a function is equivalent to minimization of minus that function. Right? So far clear? Now come out of the supervised learning world and enter the reinforcement learning world. I don't have the best actions anymore for every state. I don't have the labels like that. I have triplets of this: a state, action, reward. I have a state, do some action, get some reward. Right? So S1, A1, R1, S2, A2, R2, etc. Now what should we do? In reinforcement learning, I have total discounted reward, right? Let's maximize that. Let's maximize the total discounted reward over the horizon, right? With respect to my parameters, the parameters can be the weights of neural network. Okay. Now, again, I should use, you can either do it in this way or you can do it iteratively. What am I doing here? Here, take a look at this. At the same time that I'm maximizing my likelihood of my policy, I'm also multiplying it by the total discounted reward. Okay. Can you just notice these two? They have at least several differences. First off, in the policy, in the supervised learning, this is policy of AN star given SN, because I have the best actions per states in my data, right? But here in reinforcement learning, I don't have the best action. I have a bunch of triplets. So this is probability of AN given SN. It's not AN star. That's one thing. But should I maximize this? No. How can I trust this? Who says that AN is best for SN? That's why I scale it with this. What is this scale doing? You tell me. So, what is this scale doing? If AN for this SN is good, what happens to GN? GN was a total discounted reward. Do you remember? If action AN is good, what happens to GN? GN becomes large. The reward becomes large. So it says, consider this gradient, exaggerate it. What if the action AN is very bad, awful? GN will be low, says ignore it. Don't consider that gradient direction. Do you see that? Now you can see these two, the difference between these two. In this supervised learning, we trust the action, the best action. In reinforcement learning, who says AN is the best? Right? There is an algorithm, a famous algorithm, as one of the policy gradient algorithms. That is reinforce algorithm. Rumors say that this was the first algorithm in reinforcement learning. Okay. It was proposed in 1992. By the way, this reinforce, they wrote it in capital letters. Why? Because it's not reinforcement. It's not this is abbreviation for a lot of words. Okay. They intentionally use some words so it becomes reinforced. Okay. So reinforce algorithm is one of the very first algorithms in RL proposed in 1992. What is it? This is a policy gradient algorithm, and it uses the temporal update in equation 34, right? What is it doing? Let me tell you. It plays the game for multiply. Every time that we do, Yes, every time we do some action on the state change, on the environment, the state changes, right? Yes, yes. So whatever you do, it will impact your future. For example, I'm playing a chess game. I sacrificed my queen. Was it a good thing to do or not? Next 30 moves will say it.
But those other states, like say if you act on time, equals 0 with action, whatever action you choose,
Yeah.
policy, those other ways you act for the other time steps, is that deterministic based on your current policy?
No, see, so let me tell you in this way. Let me think. So I think this algorithm answers your question. So what am I doing? You first off, you might be wondering, how do I know the future for total discounted reward? I'm telling you that we play the game until the end once, and then we start training. So we have the future. Okay. So what am I doing? We have episodes. In every episode, I play the game once till the end. Okay. And I have the trajectory, right? As a result, for every time step, I know my total discounted reward until the end. Okay. So I use that. So I update my policy. Then I go to the next episode. I play once again. I update my policy again. I play once again. I update my policy again. Right? So reinforced algorithm is doing this. So it says that for each episode, you have a loop over the episodes, playing the game again and again. For every episode, you play once, so you know state, action, reward, triplet from the start until the end for this game. Right? You may have played well and you have won, or it was an awful game and all of the rewards will be very low, right? Then for along this trajectory of this episode, you calculate the total discounted reward. So every time step of this trajectory has some total discounted reward until the end, right? Then you do one step of gradient descent or backpropagation, and you do play the game once again. So this is iterative until convergence of the policy pi. Do you see that? So basically, if in this episode you won the chess game, for example, this update will be large because of this. If you lost, it will almost be ignored because of this GN. What if you are playing the game, chess game, you were playing very well until the middle of the trajectory episode, and suddenly something happened, you felt bad, and you played awful. Assume what happens when I say you, I mean the machine. Okay, assume something happened with the machine and it played well. So it played well until the middle, and then it played worse later. What happens? Consider that we are using GN, so G0 until GT. By the way, capital T is the number of total states actions until the end. So how many time steps I have in this episode, okay? And this capital T might change in every episode. This episode might last for 10 iterations. By 10 moves, I win the game. Or the next episode might take 50 iterations, 50 time steps. So this T depends on the episode, okay? Well, consider my example that I said. Assume until the middle of the game, I was playing well. From the middle till the end, I played awful. What happens? For G0 until GT over 2, this will be exaggerated, right? But for GT over 2 plus 1 until G capital T, it will be ignored. Yes.
But we're not for every Like after you've got all of it.
Give me a second. I understand what you're saying. I think this should be inside the for loop. Yes, because it has n subscript and it must be inside the for loop. I apologize. So basically, I'm doing. So if I have t time steps in my episode, I will do t iterations of backpropagation in this episode, and then I go to the next episode. Okay. Yes.
How do we know like at which point?
So no, wait. So first off, compare these scenarios. I play well until the end. My GN, my G0 will be good, G1 will be good, GT until GT, all of them will be good, right? If I did something bad in the middle, it will decrease GN a bit, okay? If I played awful from start until the end, my G0 until GT will be small. Almost all of the episode will be ignored for backpropagation. What if I played well until the middle and then bad until the end? Still my G0 will be better than my GT, okay? Because my GT is in the second half. My G0 is in the first half, which I played well. But my G0 in this case is less than my G0 when I played well in the whole episode. Because the second half still has effect in my G0. Right? This is total discounted reward. But I'm saying that G0 will be a bit good because of the first half, but less than the G0 in the case where all of the episode was good. Did you get it? Did you get it? Okay, this is reinforced algorithm. And at the end, you have found this W, and pi, you returned your policy. You might be saying that in 1992, we had neural network, but we didn't have deep learning. So why do you say backpropagation? I'm saying that at that time, this was considered as gradient descent. It wasn't a neural network. But in machine learning, whatever you can do with gradient descent, you can do it in neural network too. Because backpropagation is nothing but gradient descent and chain rule. Okay? Now AlphaGo. Game of Go by reinforcement learning. What is Game of Go? Game of Go is an Asian originated game from East Asia. Okay? It has 2 players. Okay? Alternatively, they place a stone on some intersection. So this is the board. The game board. It has a bunch of dots in it, right? The dots are called intersections. And you have 2 players. One player has white stones. One player has black stones. And they're all the same shape, okay? And the players can put stones on the vacant or empty intersections. Then connected stones which have no adjacent vacant intersection are removed. Okay, so you connect some, so you put the stones in a way that they become connected without any adjacent vacant intersection. Okay, by the way, I'm not an expert in this game, so for more information on the rules of this game, try to YouTube or Google it. Okay, so by the way, they put the stones like this. They don't put it like this. They usually use these 2 fingers. And the player who controls the largest intersections at the end of the game becomes the winner. In other words, every player should try to have more intersections and try to remove the intersections of the other player, something like this. This game is difficult. Why? For computers specifically. How many states does it have? It is a 19 by 19 board. So how many cells does it have? 361, right? And each cell can have 3 states, right? Either vacant, empty, or white stone or black stone. So in other words, how many possibilities do we have? 3 to the power 361, right? It's a large number. So AlphaGo, proposed in 2016, usually whenever we have alpha something, it's proposed by Google. So AlphaGo was proposed by Google. It uses deep reinforcement learning for playing the game of Go. Okay. Another alpha which is famous is what? Have you heard of it? What? Alpha Star, I think. What was it? For? I don't know. I know another one, Alpha Fold, for DNAs and genes. Okay. So they whenever they have some revolutionary thing, they call it alpha something. Okay. So AlphaGo proposed in 2016, and they are usually published in Nature. It uses deep reinforcement learning for playing the game of Go. It was done after chess. So the chess project was over, then they went to Go. Okay. So it has several networks. One network that it has, one of them is policy network. What is that? It models the policy, the probabilistic policy of a action given a state, right? It's a stochastic policy, where the input of the network is the state S. What is the state S here? The configuration of the board, right? Agreed? By the way, they don't reshape the configuration, so they use convolutional neural network. The output of the network is a distribution of the actions. They use softmax, right? So they use softmax activation function. As a result, what is the output? It says that a bunch of probabilities, right? And it's a turn of computer, right? It's a turn of computer. Assume the color of computer is white. Assume. So you have here at the end of the neural network, at the output of neural network, you have a bunch of probabilities, softmax. They sum to 1. One of them is larger, right? It means that put the stone on that cell. So you have, for example, these, you have these, you have these, you have these, you have these. And if all of them are small, it means that put the stone here in this cell. Hey, computer, put the stone here, right? And what do they do for training? They use supervised learning once. So it's a stage-wise training. In this stage, they are using supervised training. What do I mean? They have pairs of states and best actions. State, best action. In this configuration of board, what is the best action? How do they know that? By professionals. They have recorded how the professionals play the game in Asia. They have 30 million board configurations, 30 million cases where the professionals have chosen the action. But 30 million is small for this number of states. This is the best that they could do. Okay. Then, so they have a bunch of state action pairs. Now they maximize this log likelihood. How do they do that? Of course, neural network is minimizing that. So they basically use the minus. So rather than maximizing this log likelihood, they minimize the minus log likelihood. They call it negative log likelihood. Doesn't matter, right? So this was the first stage of training. Then, after this supervised learning, what do? They fine-tune this policy network using reinforcement learning algorithm. The thing that I told you, using policy gradients. Using policy gradients that I introduced to you. So, how do they do that? In the previous slide, I said they have games played by professionals configuration. In this slide, I'm saying that for policy gradient, the computer plays against itself in the previous iteration. So they do it iteratively The network is getting better and better, hopefully. We hope that the network in this iteration wins the network in the previous iteration, right? So it plays against itself in previous version or previous iteration, whatever we call it, right? Previous episode, because they are playing. So at every episode, you are playing the game once, right? So basically, you play the game against your previous episode, because in every episode you are doing backpropagation and you're tuning your neural network weights, right? As a result, in every episode, you have some neural network version. As a result, you can play with yourself. I mean, the computer can play with itself in the previous episode version. Okay. Now for policy gradient, we know that we need, for policy gradient, we need GN, total discounted reward. They made it simplified. They said, if you win, GN is 1. If you lose, GN is -1. I guess for draw, they also put -1, I guess. Okay. So, and this is one step of policy gradient. So you can use, for example, reinforced algorithm. So you, at every episode, you are training for T times, right? And you are playing against yourself in the previous episode of reinforced algorithm, for example, right? Now, third stage, another thing. So the previous two stages were serial, so in series. So they did the supervised learning first for the policy network, and then they did policy gradient. They fine-tuned that by policy gradient. In parallel, they had another network, value network. Why is it useful? I will tell you. So value network predicts the value, VS, given the state S. Okay, given this board configuration, it tells you the value V. In other words, it predicts whether it will win the game or not. If value V is large, it means that I'm in a good situation. If V is low, it means that I'm losing. Why is it useful? Can you tell me? Because I saw the documentary movie on YouTube about AlphaGo. They use this value network several times during the game. Yes. So several things. First off, if it is in a bad situation, it tries to work better. That's one way. Another thing that which I saw myself that it was used for during a game, a famous game that they had with a professional. After training, they had a game with a professional. Okay. And they used it for predicting whether they should resign or not. Because assume you are playing a chess, right? Chess game. If you are not in a good situation, you will say, let's resign, right? Hopefully the other person accepts. Otherwise, you might lose, right? That's why either you predict that you lose and you don't continue, or you resign, or you say, can we have draw? These things, right? So value network can be used for that. If you have tracked the professional chesses, they never end. Have you tracked them? Have you seen professional chess games, matches? They usually never end. Always someone says, okay, I lose. Because they can predict what happens in the future. Okay, they don't go until the end. So the input of the value network is the state S, which is the configuration of the board, and the output is the discounted summation of rewards, value. Bellman equation, right? So again, they use G, but they don't use the total discounted reward. They make it simplified. They say if it wins, G equals 1. If it loses, G equals -1. Okay? Then what do they do? This is the value network. Its output should predict G, whether it wins or loses, 1 or -1. So they use a mean squared error between these two. in the test phase, they can simply use a threshold, half, to see, because what is this? They are using a sigmoid activation function at the end. One neuron at the end, outputting a value between 0 and 1. Or hyperbolic tangent network activation function, outputting a value between -1 and 1. Okay? Then what do they do in the test phase? They can simply use the threshold 0 to see if the value is larger than 0 or smaller than 0, to see whether I'm winning or I'm losing, how awful the situation is, how good the situation is, right? So they try to minimize this loss function, and they use gradient descent or backpropagation for training, right? So this was the second network that they used. For the first network, policy network, they used supervised learning, then fine-tuned that by policy gradient. The second network was value network. Then there's a third thing, which we don't go into it because it's out of the scope of the course. That's called Monte Carlo tree search, MCTS. There can be a course on it. Okay, it's a family of methods. What do? They combine the policy network and the value network into a Monte Carlo tree search, MCTS. Let me tell you briefly what it is. Consider the tic-tac-toe game. Do you remember that? So initially, maybe the player chooses this action. Okay. Now, how many other scenarios happen for the circle? You tell me. Either circle is here, put here, or circle is put here until circle is put here. How many? 1, 2, 3, 4, 5, 6, 7, 8. 8 other cases, right? Then for this one, 7 other cases happen. Either this until either this. Also for this one, 7 other cases happen. For this one, 7 other cases happen. Again, for this one, 6 other cases happen. So it's a tree, right? It's a tree. Now, this is only for 9 cells. How many cells do we have in the game of Go? 360, right? Something like that. It's 19 by 19. It's huge. A tree becomes huge. You will have even memory error. Okay? You can't fit it in the memory. So what should you do? Time complexity will be awful to search among all of these scenarios. Memory will be also awful. So what should you do? They only grow the tree in the path that they know that probably that's the best path. So they only grow some important paths. It's a Monte Carlo tree. What do I mean? It's probabilistic. So they are not sure about it, but they hope that probably this is the best path. Let's grow in that path only, right? How do they do that? There are algorithms on that. Okay. So they basically, MCTS or Monte Carlo tree search doesn't grow the tree in all different paths and scenarios. They only tree in a specific paths. Okay. And as you can guess, it has been used for almost all of use of artificial intelligence for solving any board game, like chess. For chess, they use MCTS a lot. For Go game, they use MCTS a lot. If you see their papers, you see MCTS a lot. So, for example, it has been used in AlphaGo for game of Go. In AlphaZero is the other one for chess. AlphaZero is for chess and shogi. What is shogi? Do you know that? Japanese chess, exactly. It's a type of chess developed in Japan. Okay, so AlphaZero has been proposed for that. They use MCTS, all of them. Okay, some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo Department of Statistics. Also watch teachings of Professor Pascal Poupart at the University of Waterloo Department of Statistics. They are available on YouTube. Okay. A good textbook on reinforcement learning is by Richard Sutton. Who is Richard Sutton? You know him? He's one of the most famous guys in reinforcement learning. I think the most famous scientist in reinforcement learning is Richard Sutton. He's in Alberta, University of Alberta. Okay. You know that we have at least 3 big hubs in Canada for artificial intelligence. One of them is Vector, right? In Ontario. One of them is Mila in Quebec. One of them is Amy, AMII, I guess, in Alberta. Head of big people. Each of these has some big people. Big people in Vector. One of them was Hinton, who retired, Jeffrey Hinton. And there's a bunch of other guys too. One of them is Brendan Frey. Brendan Frey is also very famous. He was the supervisor of Algo. And did you know that Brendan Frey was a professor in University of Waterloo? He switched. He moved to University of Toronto 15 or 20 years ago. Okay? He's now University of Toronto. And a bunch of other people. By the way, Brendan Frey was also the supervisor of Ali Reza Makhzani, proposer of adversarial autoencoders. Anyways, a big guy in Mila is in Quebec. Yoshua Bengio. Yoshua Bengio has funds of millions of dollars for artificial intelligence. I heard that he has 60 students, something like that. Okay. And his famous student is Ian Goodfellow. Have you seen the deep learning book? The famous deep learning book is by Ian Goodfellow and Yoshua Bengio et al. Yoshua Bengio was a student of Hinton. Okay. A big guy in Amy, University of Alberta, is Richard Sutton. That's why Amy, University of Alberta, is focusing a lot on reinforcement learning. Okay. So, as I said, these are the references. The most famous book in reinforcement learning is by Richard Sutton in MIT Press, Reinforcement Learning, an Introduction. Okay. We have, this is multi-agent reinforcement learning. This is our tutorial paper on hidden Markov model. A survey on model-based reinforcement learning, a survey on model-free reinforcement learning. This is our tutorial paper on sampling, survey sampling, and Monte Carlo methods. This is the paper of DQN for Atari games. Do you remember? By DeepMind, playing Atari with deep reinforcement learning. This version was never published. It was in archive, but they published it under another name. If I can find it, yes, in Nature, in the year 2015, in 2 years, human level control through deep reinforcement learning. Some of the archive papers which never were published have thousands of citations. This one is, I don't remember this one. This is Mastering the Game of Go with Deep Neural Networks and Tree Search. This is in Nature. This is the paper of AlphaGo in the year 2016. A survey of Monte Carlo tree search MCTS algorithms. You can see it in this paper. Mastering chess and shogi. So this is the paper of AlphaZero in 2017. Also this one, a bunch of papers on that. A general reinforcement learning for masters of chess, shogi, and Go. Again, mastering Atari, Go, chess, and shogi by planning with a learned model. Also, it's published in Nature. Any question? No? Okay, so RL is over. In this course, I covered fundamentals of RL. You can pass courses on one semester course on RL. For example, Pascal Poupart teaches that in Department of CS, but I tried to touch the important parts for you. So the next topic is fuzzy logic, but we'll do it after the break. Let's have a break and come back at 8:25. Okay. Okay. So far, did you like the course? Yeah, great. Okay, I'm happy you liked it. And the fourth part is also very cool. Very cool. And you'll see. So we start the fourth part of the course, and that is fuzzy logic, fuzzy sets, fuzzy logic, and fuzzy inference systems. First introduction. Crisp or binary or Boolean logic. What is binary logic or Boolean logic? 0, 1, true, false, right? 0 for false, 1 for true. It was proposed by George Boole in 1815 to 1864. If I'm not wrong, according to my memory, Boole was grandfather of Hinton. Yes, Hinton is one of the grandsons of Geoffrey Hinton. I mean, is George Boole. Okay, as far as I remember, according to my memory. So George Boole was 1815 to 1864, and he proposed true-false logic, binary logic, or Boolean logic. Hence, Boolean logic is named after him, right? So the truth. What about truth table? Have you seen truth table? No. For example, x, y. This is x and y. So what does and mean? So zeros. So we have, how many cases do we have for 2 bits? 0, 0, 0, 1, 1, 0, 1, 1. And means that both of them should be 1. And so 0, 0, 0, 1. Right? This is called truth table. We can also have or. What do I mean? Or means at least one of them should be 1. Right? For example, 0, 1, 1, 1. We can have XOR. I think they denoted by this, something like this, if I remember. So XOR means exclusive OR. Only one of them should be 1, not all of them. So 0, 1, 1, 0. Right? This is called truth table. It's because it's a table. Who proposed truth table? Again, everything goes back to a philosopher, right? It was proposed by Ludwig Wittgenstein. He was a philosopher who contributed in logic. He was a logician philosopher in the previous century, one of the most famous philosophers in the world. I think he became a professor in University of Cambridge. Who approved him to be a professor in University of Cambridge in UK? Bertrand Russell. You know Russell? Russell is very famous. Just Google him. Bertrand Russell. And Gottlob Frege. These two people approved him to be a professor there. Professor of philosophy. And he proposed truth table. By the way, who was Gottlob Frege? He was a philosopher / mathematician. He proposed function. You know function in mathematics, right? We learned it in high school. What is a function in mathematics? It's a map where it can't map 1 point to several points, right? He proposed that. When you read the papers of Gottlob Frege, he was in the previous century. At the start of the previous century, okay? He died at the start of the previous century. When you read his papers, you don't know whether you are reading a paper in philosophy or mathematics. It has equations, but it is a paper in philosophy. Okay, interesting. Anyways, fuzzy logic was proposed by Lotfi Aliesker Zadeh he was alive in 1921 until 2017. He passed away several years ago. Okay. It was proposed in 1960s. It's a bit old. Okay. Who is Lotfi Ali Asgarzadeh? He's very famous. According to my memory, and as far as I know, if I might be wrong, but according to my memory, he was born in Azerbaijan. Then his family moved to Iran. He did his I think his high school and his undergrad studies in Iran. He did his undergraduate studies in University of Tehran. Then they moved to US. He or his family, I don't remember. I think for PhD studies, he went to US. And he studied in US, and then he became a professor in University of Berkeley. Who was his PhD supervisor? A very famous guy whose students were more famous than him. One of the students of his professor was Kalman. Have you heard of Kalman filter? Yeah. So Kalman and Zadeh were both students of one professor. Okay. Kalman. Can you imagine being lab mate with Kalman? Okay. Okay. So then he became very famous by proposing fuzzy logic. By the way, you might think that because he studied in Iran, so he could speak Persian. No, he forgot Persian. He couldn't speak Persian when he was in the US. By the way, because of his success, University of Tehran also gave him an honorary PhD also. So what is fuzzy logic? Fuzzy logic is a revolution against binary logic. Assume this. I ask you, how are you? You can say, I'm good, I'm bad. I'm feeling good, I'm feeling bad, right? But someone says, I'm 70% good, I'm 30% bad, right? Who says I should say only good or bad, true or false? Let me have a range, and I give you a float score between this range, in this range, right? 70% good, 30. So this is fuzzy logic, a revolution against binary logic. So fuzzy logic extends and generalizes binary logic. It's also called crisp logic because it's like crisp. It's crispy. Okay. Have you eaten chips, crispy chips? Right. It's crispy. It's true, false. Right. It breaks down between true and false. It's not float. Okay. So from levels 0 and 1 to a continuous range between 0 and 1. So 0 means completely false. 1 means completely true. Somewhere in between is somewhere in between. Closer to 0 means closer to false. Closer to 1 means closer to true. More true, more false. Right? In other words, it generalizes the binary logic to many-valued logic. So they also call fuzzy logic many-valued logic. I think fuzzy logic can be seen as a special case of many-valued logic because many-valued logic might also go beyond 1 or below 0, something. I don't know. Anyways, many-valued logic is also an important term in mathematics. Fuzzy logic is not just for engineering. Although Zadeh was in engineering, but fuzzy logic also went into mathematics. You can see fuzzy logic in pure math. Can you believe that? Okay. So in fuzzy logic, we have partial true and partial false rather than merely true and false. Okay. This imitates the human-like approximate reasoning. We humans are not 0 and 1. We have approximate reasoning. When I say do this, probably it is good for you with probability 70%. I never say that it's definitely good for you. I don't know the future, right? Many real world quantities are also subjective, approximate, and qualitative. They are not perfect. These are the intuitions why we need fuzzy logic. Now, let's introduce fuzzy sets. So just give me a second. Yes. Fuzzy sets are the building blocks and cornerstones of fuzzy logic. You can't have fuzzy logic without fuzzy sets. The whole fuzzy logic is on fuzzy sets. Okay. What is fuzzy set? It's an extension and generalization of crisp set. What is crisp set? Whatever you learned as set in high school is a crisp set. What was set? A set of values, a set of something, some stuff, right? In a crisp set, an element either is a member of the set or not. You can say this belongs to the set or not. For example, you have set S and an element A, whether it is in the set or it's not in the set, right? We learned it in high school or middle school even, right? But in a fuzzy set, an element can have partial membership. 70%, it is a member of this. 30% or not. Consider this set S. What if my element? So this is crisp set. Fuzzy set has some kind of boundary. So here it is only one set. But in fuzzy set, I have a shady boundary. When I'm here, I'm 100% in it. When I'm here, I'm 100% out of it. But when I'm here, I have partial membership. Right? But in crisp set, I'm either in it or not. Its boundary is crisp. Interesting. An example, set of tall people. This is also a philosophical question. Who is tall? We don't have a threshold. So this is crisp set, but we can't have it for tall people. So it's kind of a smooth thing. The more height you have, the taller you are. Right? Also in philosophy, this is a critical question. They say, who is bald? How many hairs should you have to call you bald or not bald? There is no specific threshold. So it's this philosophical question. The membership to a fuzzy set is a gray zone, right? For instance, in this example, there is not crisp cutoff of height for being tall, right? Do you remember Venn diagrams that we had in high school? We have it for fuzzy sets as well. So we have a universe X. So let X be a set that contains every set of interests in the context of a given class of problems, such as set of all humans. This is called universe of discourse or universe, whose elements are denoted by X, right? Then a fuzzy set A in the universe discourse X it belongs to the universe, right? It's a subset of the universe. It can be represented by a Venn diagram. So whatever you have for binary logic, you can extend it to have for fuzzy logic. So here, universe X, fuzzy set. As you see, we have a fuzzy boundary, right? Please interrupt me whenever you have any question. Every element has a degree or grade of membership in a fuzzy set, right? I told you an example. Here I'm 100% in the set. Here 100%, 0% in the set. Here partial, some maybe 30% or 70% in the set, right? So I have a grade of membership or degree of membership, right? This membership, of course, is between 0 and 1, right? Can be denoted by a membership function. So I can denote it by a function whose domain is a domain of values that the element can have, and its range is between 0 and 1. You know, do you remember domain and range of the function? Domain is the values of input that it can get. The range is the values of output that it can get, right? So the output is between 0 and 1 because it's membership. Its input is a domain of its input, whatever it can be, right? Assume X is one-dimensional. X can be a vector or a matrix. For simplicity, assume it's a one-dimensional scale, right? Then it's a map from domain of X, denoted by D of X, to 0 and 1. In other words, it maps X to mu A and X. Mu A and X is, mu means membership function, and subscript A means for the fuzzy set A. X is the element. So far clear? Right? Okay. By the way, when you don't look at me, does it mean that you're listening to me? You guys, are you listening or following, or have you lost what I'm saying? Okay, great. Example. As you see, we can have continuous membership function, discrete membership function, depending on whether the data input element is discrete or continuous. If it is continuous, examples are these, like this. As you see, domain depends on the domain of input. It can be positive domain, negative domain, a range between both negative and positive, whatever. But range is between 0 and 1. Agree? And it is continuous. It can be partially linear function or completely nonlinear function. Right? And it is a function because I can't have two memberships for one element. So it's not like this. It's not a function. Because for this value, I have a bunch of memberships. It doesn't make sense. For discrete, then my domain is also discrete. Again, it's between 0 and 1. The domain is discrete, but the range is continuous. Because range is a score of membership, degree of membership. Now, every element X has some membership in the fuzzy set A. Okay? By the way, please bear with me and follow me, because every slide depends on the previous slide. If you don't understand anything, shout at me and let me know, okay? Otherwise, you will lose the subject, okay? I'm building up gradually. I'm building up a building, okay? Every element X has some membership in the fuzzy set A, right? Therefore, the fuzzy set A can be represented as a set of ordered pairs. This is the way that we can represent this. So we can have pairs of X and its membership. We can show the set A as pairs of X and its membership, where X belongs to X in the universe, and mu AX is between 0 and 1, right? The membership shows the grade of possibility and not probability. This is important. Yes. Can you explain more?
Because it's not in the actual.
Okay, I understand. So you're saying that what if X is in the universe, but it is not in the set A? Its membership is 0, right?
Yeah.
So in this case, we can say X and comma 0, but we usually don't show them. By default, we can we don't show them. Let me tell you in this way. If we, in this notation, we can only show X and the mu ones which are greater than or greater than 0. You can show all of them. Okay, but it doesn't need to, you don't need to show the ones which have membership 0. But in membership function, for the whole domain of universe, you do that. Why? For example, the domain of universe is between, in the scalar, it's a scalar. I'm assuming it's a scalar, it can be vector or whatever, 0 and 10, okay, then my membership can be like this. What does it mean? For 0 until 4, I have membership 0. For 4 until 5, I have partial membership. For 5 until 10, I have complete membership. This is basically like a set with a fuzzy boundary. This is complete membership. This boundary is partial membership. Outside of the set is this. Clear? What do you mean by curve? Circle bracket. No. This is not a range. You mean membership 0? I'm saying that you can put it, but it's redundant. We can say for this notation, we can say I disregard the elements which have membership 0. You can put that. But when by default, when you don't put them in the set, it means that their membership is 0. Okay. I understand what a square and circular bracket is, but I didn't understand how it is related to here. But we can talk about it offline. Okay. Oh, okay. I get your point. Anyways, the range of membership is a square 0 and 1. Okay, so it has 0 in it and 1 in it. Completely not being member, completely being member, partial membership. All of them are in the membership. I told you an example. Okay. Another thing which is important is that this membership is between 0 and 1, right? So you might think that it is probability. It is not. Why? It is not probability. Because they don't sum to 1. These values, they don't sum to 1. Or in continuous form, this doesn't integrate to 1. It's not a probability density function. As a result, we say that it's possibility. It's not probability. Okay? It's possibility. Okay? Its maximum can go until 1, but they don't necessarily sum to 1. They are all between 0 and 1. But a crisp set is a special case of a fuzzy set where the membership function can take only values 0 and 1. Do you agree? If the membership function can get 0 and 1, it means that true or false, right? So false or true. It means that it's a crisp set. We have another representation. So we have a bunch of representations, notations in fuzzy logic. I'm telling you one by one. Okay. The other one is symbolic representation in this way. If the universe of discourse is discrete with elements x1 to xn, okay, the fuzzy set A can also be denoted by this notation. So mu A x1 over x1. So you have fractions where the numerator is a membership, great. The denominator is the element. So one notation was this paired one. The other one is this one, okay? And you sum them up. This sum doesn't mean summation. This is just notation, okay? This fraction is not a fraction. This is just notation, okay? Again, back to your question. What happens if one x has membership 0? I can put it or I can disregard it. If I don't put it, I'm telling the reader that its membership is 0. Okay? Did you understand what I'm saying? Consider some x, its membership is 0. I can say 0 over that x, or I can completely don't write it. If I don't write that for that x, it means that its membership is 0. Okay? That's one thing. This summation can also be written with this summation symbol, right? But it doesn't mean summation. It's just notation. Did you understand? They built some notation out of the existing notations in mathematics. So it's summation of fractions, but this is not fraction and this is not summation. It's just notation. Okay? What if the universe is continuous? We still have the fraction, but the summation is integral. But this is not an integral. This is just a notation. Yes. Mu is the membership, which can be represented by a membership function, right? So mu ax is the value of membership function for the input x, right? Again, I use this for x is in the universe x, right? But this doesn't mean integration. This is just notation. And I think it's obvious. Why? Because I don't have dx here. Do I have dx here? Differential of x? No. And you know in mathematics, if you put integral without a differential, the professors in departments of mathematics will get crazy, right? Integral sign without differential doesn't make sense in mathematics, right? But here in fuzzy, we don't put dx because it's not an integral, okay? This is called symbolic representation. Example, discrete fuzzy set, this. We can show A with, so that 1, its membership is 0. So I can completely ignore it. Or I can write 0/1. For 2, its membership is 20.25. This is fraction, right? What happened? This is fraction. Right? For 3, its membership is half. For 4, its membership is 1. It doesn't mean 1/4, which is 20.25. It means that 4, its membership is 1. 5, its membership is half, and 6, its membership is 0.25. 7 doesn't have any membership, it's 0. For continuous fuzzy set, this is an example. Assume, by the way, what is this? Can you tell me this? What is this membership? It's a fuzzy representation of digit 4. Because for digit 4, membership is 1. 3 is closer to 4. Its membership is half. 5 is also closer to 4. Its membership is half. 2 and 6 are further away, but 1 and 7 are very far. It's a fuzzy member. So if it was crisp membership of 4, it would be like this. But when it is fuzzy, it became like this, but in discrete form. Right? Fuzzy membership of 4. Representation of 4. Digit 4. Now, continuous form of representing the value a, and this value a might be a float value. It might not. It might be integer or float, whatever. So we can say its membership. This is this function centered at a. You don't believe me? Plot it by computer, by Python, and you will see it becomes like this. I think it's obvious. At a, set x to a, it becomes 1/1. Its membership is 1. The further you go away from a, the less it becomes, and the power is 10. It's an even power, so it's symmetric around a, right? Agreed? And again, by symbolic representation, I write it as x and, sorry, I apologize. It should be 1/, I apologize. This, okay? This is symbolic representation. Sometimes when I'm preparing the slides, I'm tired. Okay, I make typos. Okay, anyways, did you get it? The whole thing? And this is a continuous fuzzy representation of A. Okay. Now, let's review the well-known membership functions. triangular membership function. What is that? It's basically this figure. Okay. Again, as you see, its range is between 0 and 1. This is the whole domain of X. We might have some 0 memberships or might not, depending on A and C. If you set A to be a start of the domain, then you will not have this part. It will start from here, right? So you have 3 values, A, B, C, to represent this triangle. At B, it becomes 1, right? Usually, not always, but most often, the membership functions reach 1. Okay, so at least in some points we say that it has complete membership. Okay, so before A, it is 0. Between A and B, this is the equation of this line. This. Between B and C, this is the equation of this line. After C, it's 0. You can also write this formula as this. Maximum of this and 0, because this can get negative too, and we don't want to become negative. And this part is this. Okay. Also, of course, A is less than or equal to B, and B is less than or equal to C. Okay. Another one is trapezoidal sorry, trapezoidal membership function. And what is that? Is this, right? It's between 0 and 1 again on the domain, but it has 4 values now: A, B, C, D, 4 parameters. Again, less than A, it's 0. Between A and B, it's this line. Between B and C, it's 1. Between C and D, it's this line. Over D is 0. A is less than B, B is less than C, and C is less than D. Less than or equal to, I mean. Right? As a result, you can have a rectangular membership function. No, you can't have rectangular. Why? Because it needs to be a function. It needs to be a function. I think, to be more specific, I should be strictly less than, and D should be. But B and C can be equal to each other. Why? If you set B and C equal to each other, it becomes triangular membership function. But A and B should not be equal to each other because it is a function. You can't have several memberships for one value. Okay? We can have Gaussian membership function. So what is this? Exponential operator. It is very similar to the probability density function of Gaussian distribution, but it doesn't sum to 1. It doesn't integrate to 1 because we don't want it to integrate to 1. The only thing is that at the center C, or mean C, I want its membership to be 1. And it happens. Set X to C, it becomes e to the power 0, which is 1. Right? And it has a standard deviation sigma, or variance sigma squared. Right? So C is the mean, and sigma squared is the variance of the Gaussian function. Its integral is not 1, so it's not a probability density function. Right? And at C, it becomes 1. Another one, which is famous, is generalized Bell. It's also called Bell in simple words. Bell or generalized Bell membership function. What is that? It's this. Equation 8. Its figure is like this. So it's kind of similar to Gaussian, but it has some part which is flat at the top. It's like a Gaussian that you have put a hammer on it. Okay? And it has several parameters, A, B, and C. A, B, and C. Sorry, this is C. C here is the mean of the bell here. You see, C is the mean of the bell. What about A and B? They both control the slope of the bell and heaviness of its tail. What do I mean? A slope of the bell is this. Whether it's like this or this, okay? This is a slope. By the way, these two slopes are opposite of each other. See my hand? Whether it's like this or this. Also, what is heaviness of tail? What do I mean by heaviness of tail? Give me a sec. This. How soon it goes to 0. Whether it has heavy tails or not. Yes. Okay. These are slow. So consider this. Let's analyze it. In the middle is C. Okay. Then here C plus A. At C plus A, its membership becomes half. At C minus A is also its membership becomes half. So this distance is A. This distance is A. So the whole thing here is 2A. And at C plus A, its slope is minus B over 2A. And this slope at C minus A, its slope is B over 2A. Okay? So far clear? Now let's play around with these parameters and see how it changes. If you change A equals 1 is this, A equals 2 is this. In other words, the larger the A, the heavier the tail. The heavier the bumpier or heavier the bell. Okay? The fatter the bell. Change B. This is B equals 1, B equals 2. The larger the B, it means the more hammer you have used on top of the bell. The flatter the top of the bell. Okay? The change of C will shift the bell, the mean of the bell. The change of A and B together is this. A equals 3 and B equals 2 is this. Now let's increase both A and B. It becomes like this. So it becomes fatter in general. Okay? Its behavior is interesting, weird and interesting. Okay? So, by the way, you might say, I only introduced continuous membership functions to you. Quantize this and it becomes discrete. Okay? So this is bell. You can have discrete bell. You have Gaussian, you can have discrete Gaussian. You have triangle, you can have discrete triangle. Right? Now, each of the membership functions has its own pros and cons. The triangular and trapezoidal membership functions. Their benefit is that they're partially linear, so they are easy to compute. Easy to compute the membership value. But this also is a problem because they are not smooth at the intersections of the linear parts, so they are not very suitable for gradient descent and optimization if you want to use optimization. The other way around, Gaussian and Bell functions are smooth, so they are good for optimization, but they are hard to compute the membership value because they are not linear, right? Their own pros and cons, it's a trade-off. Now we have a bunch of now fuzzy set is almost over. Now let's go to fuzzy logic. If we were in a crisp binary logic, I would have taught you what and or not XOR these things. Have you passed any course on logic? Yeah. At least 2 types of the students pass logic. engineering students and slash mathematicians, and philosophers. Philosophers also pass logic course. Okay. So here, similar to that, we have fuzzy logic operations, similar to and or not, right? Let's see. There exist operations on fuzzy sets similar to the operations on crisp sets. A fuzzy logic operation is an operation which is applied to one or multiple membership functions, but it outputs one membership function. So its input is one or several membership functions, its output is one membership function. Similar to and gets two or more than two inputs, it outputs one thing, 0 and 1, right? So in other words, it gets a bunch of membership functions between 0 and 1, and it maps to one membership function between 0 and 1, right? The most important operations in what happened? The microphone got tired. What are the main operations in binary logic? There are three main operations. And or not. You can make any other operation out of these three. And or not, right? Here, likewise, we have and or not, but and you can see it as intersection. The intersection, because we have sets here, right? The intersection of sets. Intersection is called T-norm. Names, T-norm, okay. Or, so this is like and. Or is like union of sets, right? It's called S-norm. Not is complement of the set, right? Now let's go over them one by one. T-norm. The intersection of two fuzzy sets is performed by T-norm operator. What does it do? First off, intersection is denoted by this, right? Agreed? This is intersection of two sets, right? And these are now fuzzy sets with fuzzy boundaries. A and B, two fuzzy sets. Membership function of intersection of A and B is denoted by T of T-norm of mu A and mu B. They also denoted by mu A T mu B. It's notation. Okay? So you can put T in the middle. There are several properties. So there are a lot of T-norms, not one T-norm. Okay? Whoever wants to propose a T-norm, a new T-norm, they should satisfy these four things. It has four properties. Non-decreasing. What does it mean? If A is less than or equal to B and C is less than or equal to D, then the T-norm of A and C must be less than or equal to the T-norm of B and D. Okay? It should satisfy commutativity. What does it mean? Basically the order. The order can change. ATB equals BTA. So it's not sensitive to order. Right? Associativity. What does it mean? ATB first, and the result take the T-norm with C. Another time, take the T-norm between B and C, and then the result, take the T-norm with A. So in other words, change the parentheses. It shouldn't change. Right? It shouldn't change. So let me tell you in the three formats. A, B, then the result, take it with C. It shouldn't matter whether you do A, then B, C, you take it in this way. So these two are equivalent. Okay? Boundary conditions. What do I mean? What are the boundaries? False and true. Complete false, complete true. 0 and 1. Boundaries of membership, right? Boundary of fuzzy becomes binary, crisp, right? So the T norm of A and 0 should be 0. I think it's obvious. Why? Because it's an intersection. Intersection of a set and 0 should be 0, right? Intersection of A and everything, a true, should be A itself, right? Right? Kind of, you can see intersection as lower bound, kind of, and union or S norm as upper bound. I'm saying that kind of, okay? So according to what I just said, one of the most famous T norms is minimum of them. Okay, minimum of them. So T norm of A and B, you can see that as minimum of A and B. They denote minimum in the literature by this wedge 2. Okay. So whenever we use wedge, we mean minimum T norm. There are a bunch of other T norms too. As you can see, first off, they all satisfy these 4 properties, and they are kind of the intuition of lower bound. Let's see. Algebraic product. You can see it as A times B. Bounded product. You can see it as A plus B minus 1. You know that A and B are between 0 and 1. So A and B is between 0 and 2. Minus 1 becomes between 0 and 1. Then take the maximum of that with 0. This is maximum. So wedge means maximum, minimum. V means maximum. Okay. This is S norm. So another one is basic product. T of A and B, you can see it again, the intuition of lower bound. If B is 1, completely true, the T norm becomes the other one, A. If A is 1, complete true, the T norm becomes B, because B can be between 0 and 1. If both are less than 1, then you let it be 0. Let T norm be 0. You can check each of these properties and they should satisfy all of them. Okay. General form, we have also general forms. General form 1 and 2. So T of A and B with some parameter P, which is greater than or equal to 1, is this big formula. 1 minus minimum of 1 and this property. So 1 minus A is between 0 and 1. 1 minus A is also between 0 and 1. To the power P, as P is greater than or equal to 1, you know that every scalar between 0 and 1 to the power greater than 1, again, is still between 0 and 1. Right? Agree? Half to the power 4 is 1 over 16. Half to the power 2 is 1 over 4. Is again between 0 and 1. Right? So this is between 0 and 1. This is also between 0 and 1. Their summation depends on P, but it can be, in the worst case, it can be between 0 and 2, but it will never be between 0 and 2, because when you take to the power P, it becomes very small number. Anyways, again, we have to the power 1 over P. The whole thing becomes something, it might go above 1. So for us to cap it between 0 and 1, we take minimum of this and 1. Then 1 minus that. Okay? I know it's a big formula, but it's one of the T norms, general form. Another one has a parameter lambda, greater than or equal to minus 1. What is that? It's lambda plus 1. So lambda plus 1 is greater than 0. AB minus 1. A is between 0 and 1. B between 0 and 1. A and plus B between 0 and 2. A plus B minus 1 is between 0 and 1. So something greater than 0 times something between 0 and 1 minus something greater than 0. A and B are both between 0 and 1. So A times B is between 0 and 1. The whole thing might become negative. So the whole thing may become negative. So we maximum it with 0. Right? What is the most common T-norm among all of these? The mean operator. People are lazy. They use minimum operator. Okay? And it works well. S norm is the union of two sets, again denoted by this time, this, and it is denoted by S of mu A and mu B, or mu A S mu B. Okay? Different notations. It should satisfy these 4 properties. First, non-decreasing. So if A is less than or equal to B and C is less than or equal to D, ASC should be less than or equal to BSD. Okay. By the way, why am I only considering scalars A and B? Because the S norm is between membership functions, and we know that the output of membership function is a scalar between 0 and 1. Right? Commutativity. So it doesn't care about order. ASB is equal to BSA. Associativity. Again, doesn't care about parentheses. ASB then SC equals ASBSC. Okay? Bounded conditions. Now you tell me. You can see S norm kind of as upper bound. AS0, 0 is nothing, false. So it becomes A itself. But AS1, 1 is greater, upper bound. So it becomes 1. Right? Well-known S norms, as you can guess, the simplest one is maximum, AVB. Okay? Algebraic sum, A plus B minus AB. Bounded product. By the way, we engineers, we usually like these simple ones. But if you go to pure math departments, they might use these things, algebraic sum or algebraic product. Okay? Bounded product. What is it? A plus B becomes between 0 and 2. But I don't know why there might be some typo here, but anyway, I read it from somewhere, but I think it has some typo because A plus B might go above 1. Anyways, it's minimum with 1. It's a wedge with 1. Basic product. What is that? Now consider the intuition of upper bound. If B is 0, so it becomes A. If A is 0, it becomes B. If both of them are less than 1, then it becomes 1 because it's upper bound. Right? General form 1, it's minimum of 1 and this thing. What is this? A to the power, A is between 0 and 1. P is greater than or equal to 1. So A to the power P becomes between 0 and 1. B to the power P becomes between 0 and 1. Sum them to the power A over P. When I say A over P, it means a square, no, the root of P, right? Then it might go above 1. So minimum it with 1. The other general form for lambda greater than or equal to -1 is A plus B plus, so this A plus B is between 0 and 2. Lambda AB is between 0 and 1. The whole thing might go above. The whole thing might go above 1, so I use minimum of 1 and that. So if it goes above 1, it means the S norm becomes 1. Obvious, right? Now, what is the most common S norm? As you can guess, it's max operator. We are lazy, right? Complement. The complement, we can denote it by A bar, right? So, or co for complement of mu AX. So A bar denotes the complement of the set A. The properties are 3 properties. Non-increasing, this time is non-increasing. involutive, and boundary conditions. Non-increasing means that if A is less than or equal to B, by the way, it has one input, one membership function this time, complement, like not. Is A, if A is less than or equal to B, complement of A is greater than or equal to complement of B, because it's complement. It is involutive, so complement of A becomes A. They cancel each other. Boundary conditions. By the way, involutive also means that you can regret. You can cancel your operation. If it is not involutive, you can't regret. Okay. Boundary conditions. Complement of 0 becomes 1. Complement of 1 becomes 0. Well-known complement operators. Regular complement is 1 over A. 1 minus A, sorry. 1 minus. A is between 0 and 1. 1 minus A is also between 0 and 1. Sugeno's complement. Sugeno was one of the most famous scientists in fuzzy logic. He proposed 1 minus A over 1 plus PA. P is between -1 and infinity. So 1 minus A is between 0 and 1. A is between 0 and 1. So PA becomes between something. So 1 over PA, I think the whole fraction becomes between 0 and 1. Okay. You need to calculate it. There is no time for me to calculate. Jaeger's complement is, Jaeger is another scientist in fuzzy logic. For P between 0 and 1, its complement is 1 minus A to the power P, then the whole thing to the power 1 over P. Of course, A is between 0 and 1. A to the power P is between 0 and 1. 1 minus A to the power P is between 0 and 1. To the power 1 over P is between 0 and 1. And the most common complement is the regular complement. 1 minus A. We are lazy, right? Okay. So we covered these things. Let me show you some examples, and this is the last slide of this today. So let's see as visualization. We have mu A and mu B. Okay. For each of the values of X, I have 1 mu A, 1 mu B. I can do it for each value of X, or I can say for the whole membership function. Let's find the S norm, T norm, and complement. So S norm means, let's use maximum. Let's use the maximum. So here, mu B is larger, so I use mu B. Then here, mu A is larger, so I use mu A. Here, mu A is larger, mu A. Mu A is larger, mu A. Mu B is larger than this, mu B. Mu B is larger, mu B. Max. What is T norm? T norm is the other way around, minimum. Here, mu B is mu A is smaller, mu A. Mu A is smaller, mu A. Mu B is smaller, mu B. Mu A is smaller, mu A. And that's it. What about complement of what? So complement gets one membership function. Complement of this, you tell me. Here, between A and B, it is 0. Complement becomes 1. Here, I have this line. Another line, the line with opposite slope becomes complement. Here, it is 1. Its complement is 0. Here, it is this line. It becomes this. Here, it's half. Membership is half. 1 minus half is, again, half. For half, the complement is equal to itself. Here, and that's it. Right? By the way, don't get confused when I write this. It basically means that end of membership function. It doesn't mean that here it's not function. I don't mean that. Okay. Okay, thank you. We will continue it in the next session. Thank you.